So I would like to go over some of the things that we didn't get to in class today. Um, let's see. So we discussed how L'Hopital's rule can be used to determine whether or not a sequence converges or diverges. We showed how E, Euler's constant, is the limit of a particular sequence, right? And so that would be E equals the limit as n goes to infinity of 1 plus 1 over n to the n. Now, I wanted to, at the beginning of the week, I gave a little bit of a teaser to talk about uh, the area of the Sierpinski triangle, right? So we have this sequence of objects that we can draw. It begins just with a pretend that's an equilateral triangle here, right? And you can iterate. Let me fill this in quickly. We can iterate on this construction by removing the inner quarter right here. And that gives us three kind of triangles stacked on top of each other. As one student astutely pointed out, was quite similar to a popular video game icon, right? And so we can keep doing this, right? Now that we've got this little Triforce shape, we can do it again. And we wind up with 9 of these little rectangle or little triangles stacked on top of each other. Now, we can give the area of each one of these a place in a sequence, right? So let's call the area of this one A1. And well, we want to find A1, so let's do that up here. So the area of an equilateral triangle is, well, assuming the base has length 1, the height of an equilateral triangle will be, I believe, root 3 over 2, right? And we can figure that, right? Since each edge is the same, right? If we divide this in half, we have the hypotenuse on the right side having length 1, the base of this half triangle having length 1/2, then we can use the Pythagorean identity to get the height of this thing, which is right here. Right, and so that will be h, which is going to be 1/2 squared plus h squared equals 1, or h equals the square root of 1 minus a quarter, right, which is root 3 over 2, right? And so we can say that the height, or the area rather, of this whole triangle, then back over our first iteration, is just going to be 1/2 the base, which is 1, times the height, which is root 3 over 2, right? Or, right, it'll be root 3 over 4. Now to find the area of the second part of this sequence, right, we need to kind of notice that we've removed a quarter of the original. And so we're going to wind up with a recurrence relation, right? And so the area, the blackened area of this second stack of triangles is just going to be 3/4 uh, the the area of the first one, right? And if we look at A3, the area of the third stack, you can see kind of the same thing is happening. And so this winds up being a geometric recursion. You'll see right there how it works out. And in general, if we use this process to remove uh, chunks of triangles n times, right? I'll draw one more for effect, I suppose. Only because it's mostly just because it's fun drawing these things, right? Right. Hopefully that'll be enough. Uh, we'll evacuate the interior of these. This will clean up okay in a second. Right. Once we fill it in, it'll all look hunky-dory. There we go. That looks okay. Yeah. And so I suppose those triangles could look a little larger, but you can imagine that the area of this thing is going to be exactly 3/4 of the previous one. Right. And so if we look at the trajectory of that, right, we notice that we have a sequence here. It's a geometric sequence. And right, uh, in general, we have that a sub n is going to be √3/4, right? Um, Times 3/4 to the n minus 1. Right? Because A1 in this case, there is no 3/4. So you could say that it's 3/4 to the 0. And then likewise, A2 is going to have 3/4 to the 1, and so on. Right? You got, yeah. Now, what does this mean for the area of this shape? Right? So the limit, we can look at the long-term behavior of this, and we see that if we examine this, this is a geometric series, and because our ratio is less than 1, right? 3/4 is less than 1, and we know that even if it happens slowly, this sequence is going to converge to 0, right? So maybe somewhat disappointingly, this shape has no area whatsoever. Something about it just dissolves and removes uh, all area. And now let's take a look at a second sequence that we can extract from this, right? Let's take a look at the perimeter of this shape, right? And then we start out exactly the same. In fact, let me just copy and paste everything. This is the benefit of giving a digital lecture, I suppose. Right. Now let me conclude this up here. So uh, the area of the let me see if I spell this right. The Sierpinski triangle is 0, right? So that's the conclusion that we can make. But when we look at the perimeter, we see something pretty fascinating happen, right? So let's deduce what the perimeter is for the first few terms, and then we can extract a pattern from that, right? The perimeter of this first one, right? Just we assume that each side has length 1, and so the perimeter of this first thing is just going to be, well, it's going to be 3 sides of the same length. So it's going to be 3, right? And so we could say that the first perimeter is just equal to 3, right? And we'll kind of shove that up there. Now, let's take a look at P2, right? Well, that's going to have this outer perimeter still, right? So it's going to have a perimeter of at least 3, but then it's also going to have this internal perimeter, right? And what's that going to be, right? So if the way to find that out, right? If we analyze this edge of this triangle here, well, that's got to be the same as this outer this edge, right? These are equilateral triangles, remember? So this edge here has to be the same as this edge. And we know that this little edge right here is half the whole edge, right? And so each internal edge here has length 1/2, and there are 3 of them, right? So this is going to be 3 plus 3/2, right? And so this has actually got quite a bit more uh, perimeter than the first iteration of the Sierpinski triangle. Now, if we continue on, we see again, right? We have the outer edge, right? So our outer perimeter, we've got that innermost perimeter here. And so we know that that P3 is going to contain all of P2's perimeter. And then it's going to contain 3 more tiny little triangles, each one an equilateral triangle that has sides of length 1/4, right? And so this will be 3, because for the 3 triangles, and then 3/4, right? Because there's got to add up each individual side. And so that's 1/4, 2/4, 3/4. Right. And doing one more just for the heck of it, right? We can already see that it's going to contain all of the perimeter of the inside of the previous term. And it's also going to contain, right? We got to probably zoom in a little bit, right? But it's going to have 9 tiny, tiny triangles, right? Each one having sides of length 1/8 this time, right? And there's going to be 9 of them. It's going to have 9 triangles with perimeter 3/8. Now, if we start moving backwards and removing these P2s, right? So we start out with P1 equal to 3. P2 we can say is really equal to 9/2, right? And then P3, well, we got to do a little bit of arithmetic now. It's going to be 9/2 plus 9/4, which is really going to be 27/4, right? And then P4 is going to be 27/4 plus 27/8, or, right, this is going to be 54 plus 27/8, or 81/8. And so the perimeter looks like it's increasing pretty substantially. And in fact, if we kind of suss it out, and if we, after doing a little bit of analysis, we see that in general, Pn is the perimeter for the nth Sierpinski term is going to be 3 to the n over 2 to the n minus 1. Right? And that fits each one here, right? So this one is 3 to the 1 over 2 to the 0, right? This is 3 to the 2 over 2 to the 1. And then we have 3 to the 3 over 2 to the 2. And then 3 to the 4 over 2 to the 3, right? And so in general, the perimeter of the Sierpinski triangle is going to be 3 to the n over 2 to the n minus 1. Now, we take the limit on this, and we can get the overall perimeter. Right? So that'll be the limit as n goes to infinity of 3 to the n over 2 to the n minus 1. Because we've got ourselves here a term in the numerator which dominates the term in the denominator. Right? We know that this thing is going to diverge to positive infinity. Right? Now, that's pretty remarkable. Now, we've constructed this shape that has no area, but it has an infinitely long perimeter, which, when speaking of general geometric shapes, tends to defy what we expect from geometry, right? So we've constructed this dandy little shape with infinite perimeter and 0 area. Right? And now when you're playing The Legend of Zelda, you can ponder the depths of the shapes that have been provided to you. So that was the example that I had to skip before getting to infinite series, which I was really unhappy about. I'm glad I got a chance to do this. Um, but things that we covered in class, right? Well, we'll move on to that. So this is infinite series. right? And this is basically what you want is when you want to add up the terms of a sequence. And so given some sequence a sub n, and n will either go from 0 or 1 up to infinity. Its series is going to be, we're going to use sigma notation for this. It'll be the sum of from n equals 1 to infinity of a sub n. And we'll move this down, right? And so this is really just a1 plus a2 plus a3, and so on and so on. Now, these things we want to be able to figure out, we want to be able to analyze these objects. It would be handy to know if the sum that we're looking at is finite, or if it diverges, or if it somehow oscillates in some way. And one of the great tools to be able to do that is something called a kth partial sum. Right? And this is denoted S sub k, and all it is going to be the sum from n equals 1 to k of our sequence. Right? And we'll give it a little colon equals, meaning it's defined as. But yeah, so in class we did a quick example using the harmonic series, right? And so we can take a look at that quick. Right? If we were to examine the entire harmonic series, this would be the sum of 1 over n, which is going to be 1 plus 1/2 plus a third, and on and on and on. Right? But we can take a look at the kth partial sums of these, and we'll get S1, S2, S3, S4. Right? S1 is just going to be the first term, right? So that's just going to be 1. S2 is going to be the sum of the first two terms, right? So it's going to be 1 plus a half, be 3/2. And likewise, S3 is going to be the sum of the first three terms. So that, what is that? That's 6/6 plus 3/6 plus 2/6. That's going to be 6, 3, and 2 is 11/6. Right? And so on, right? Like I don't feel like doing that, so I'm just going to write it out, right? When in doubt, just write the terms out. Now, it'd be interesting to know how we could use this to tell if a series diverges. Uh, Particularly, that's what kth partial sums are good for. And so let's see it in action. All right, we'll work on with maybe a more elementary example to start, and then we'll build back up to the harmonic series. But for now, All right, let's take a look at the infinite series of n over n plus 1. Right, and it's not immediately obvious that this thing will diverge, but it turns out that it does. And so how do we know that? Well, we can use the following theorem, which I'm going to make a little bit of room for, which is this theorem. So if the sequence of partial sums diverges, right? So if the sequence of partial sums diverges, then the series diverges. The corresponding series diverges. And now let's take a look at an example of this in action. Right? So let's take a look at S1. Well, that's going to be 1 over 2, right? I plug 1 in here, 1 in here. That'll just give us 1/2, right? S2 is going to equal 1/2 plus our second term is going to be 2 over 3, right? 2 over 2 plus 1. And oops, there's nothing there. S3, our third partial sum, it's going to be, well, it'll be 1/2 plus 2/3 plus, right, 3/4. And let's do one more, right? So S4 will be 1/2 plus 2/3 plus 3/4 plus 4/5. Right? If I plug 4 in, it'll be 4 on the top and then 4 plus 1 on the bottom, right? Okay. So what can we see about this? Well, what we can notice is maybe an interesting little pet tendency that each term inside the partial sum is greater than 1/2, right? It always starts out at 1/2, and then it's always adding a bunch of things that are greater than 1/2. And so we know that S4, for instance, is going to be greater than 4 times 1/2. S3 is going to be greater than 3 times 1/2, and so on. And so in general, we can extrapolate, right, that Sn is going to be greater than n over 2, right? Or n times 1/2. And so the limit as n goes to infinity of Sn is going to be greater than the limit as n goes to infinity of n over 2. But that diverges, right? And so Sn, the limit of that is going to be greater than the limit of something which diverges. And so we can conclude, right, that the limit of this sequence also diverges. So the partial sums diverge. The partial sums of this series diverge. And then according to our theorem, right, that means the series diverges. Right? Therefore, the series diverges. Let's take a look at that. Now let's take a look at some other series and then take a look at the behavior of them, right? The more examples you have under your belt, the better off you'll be. Right, so let's take a look at the series that is -1 to the n. Right, and so that'll be equal to 1, -1, +1, -1, +1, -1, and so on. Right, and we kind of get the sense that this thing isn't going to converge, right? But we want to use the principles that were given in order to justify that. And so let's build out our sequence of partial sums, right? So S1 is just going to be that first term. S2 is going to be the sum of the first two terms, but that'll be 0. The sum of the first three terms then is going to be 1 again, and so on, right? So S4 is going to be 0, S5 is going to be 1, and so on and so forth. And so we can see that the sequence of partial sums here winds up diverging. And so we know because of that, because the sequence of partial sums diverges, we know that the series diverges. And so again, right, -1 to the n gives us grief. And so now let's do one more example. Right, and that will be the sum from n equals 1 to infinity of n over, oh, nope, not that, 1 over n times n plus 1. Right, and we can see that our first partial sum, well, that's going to be 1/2. S2 is going to be 1/2 plus 1/6, right? As 2, that's going to be 2 times 3, right? So that's 1/6. Now that's going to wind up being, right, 4/6, or 2/3, right? S3 is going to be, right, well, it's going to be 1/2 plus 1/6. And now if we plug 3 in, right, it'll be 3 times 4 down here. So this will be 1/12. Right? And this all winds up being 3/4. Right? And let me actually run that out for you. So it's going to be 4/6 plus 1/12, which is equal to 5/12. Oh, sorry. Going to be equal to 8/12 plus 1/12, or 9/12, which is 3/4. Right, and we can see that as the partial sum increases, we get this pattern where the numerator is increasing by 1, and likewise the denominator is increasing by 1. Right, and so in general, the kth partial sum is just going to be n over n plus 1. Now, if we take the limit of this, right, we get exactly, right, the infinite sum. And we know the limit of this kth partial sum, or the sequence of kth partial sums, is just going to converge to 1. And so we know that this infinite series, right, when we add all of the terms together, is going to add up to 1. Now I want to talk now about maybe one of the more fascinating accounts of a divergent series. Right, and that is the harmonic series. Right, and it'll look just like this. Right, and it'll be 1 plus 1/2 plus 1/3, a quarter, and so on. And there's something pretty wild happening here. And it is that this thing grows incredibly slowly, but it never stops growing. And if I were to just I'll just supply you with a few examples of kth partial sums, right? S1 is going to be 1. S2 is 3/2. And we'll skip down a bit. And I've done these calculations ahead of time. S10 is approximately 2.9. S1000 is approximately 7.5. And S sub 1 million is just about 14.3. Right? So it is growing very slowly. And yet I claim that it diverges. Right? And how can I make such a claim? Right? And it's because we can find a subsequence of the kth partial sums that does diverge, and it's a little more obvious that it diverges. So I say, why does this diverge? Right, and so we'll consider S4, right, which is going to be 1 plus 1/2 plus 1/3 plus 1/4. Now my claim, and let me move this down a little bit so I can make this claim, that this is greater than 1 plus 1/2 plus 1/4 plus 1/4, right? Everything's the same, these three. The only difference is that S4 has 1/3 here and it has 1/4 over here. And we know 1/3 is greater than 1/4. And so S4 is going to be greater than this whole thing, right? Which we can rewrite, right? We can rewrite this as 1 plus 1/2 plus 1/2. Now, the next one that I want to look at is S8. Right? And let's see if I left myself enough room to write this out. Now we're going to play the same game, right? This is going to be greater than 1 plus a half, uh, plus 1/4 plus 1/4, right? And that's dominating this. And then all of these terms are all greater than or equal to 1/8. And so we can rewrite each one of these. Right? And now we know S8 is going to be greater than this term, right? This thing that we've created, which is equal to 1 plus a half plus a half plus a half, right? Now we can kind of compactify this. Scooch everything over just a hair, right? So our S4 is really equal to 1 plus 2 times 1/2. S8, or sorry, S4 is going to be greater than, right? 1 plus 2 times 1/2. S8 is going to be greater than 1 plus 3 times 1/2, right? And in general, if I have any kth, uh, basically any kth partial sum of the form 2 to the k, that is a power of 2, right? S sub 2 k to the k is always going to be greater than 1 plus k times 1/2. Right? And so this sequence, the sequence of kth partial sums, contains a subsequence that we know is greater than this 1 over or 1 plus k over 2, right? And the limit as k goes to infinity of 1 plus k over 2 diverges. It goes straight to infinity. Right? And that means, right? That means S sub n also tends toward infinity, which implies what we originally set out to show, which was that the harmonic series diverges, which is it's really wild to think about, right? Because if you look, these things are increasing so slowly. You don't really think that they would ever, you wouldn't think they would ever go anywhere. But it turns out if you make your partial sum large enough, have a large enough number of terms, then it will in fact diverge. And this theorem that we discussed earlier, right? If the sequence of partial sums diverges, then the corresponding series diverges, right? So really, this is a pretty powerful theorem that we can work with. Now I'm gonna take us back. Yeah. And now I have one more very common series that I want to talk about today, right? And I want to talk about when geometric series converge. So this is the convergence of geometric series, right? And so we want to see when it diverges. And so we'll explore that first because these ones are fairly straightforward, right? Now let's ponder this. Let's recall that a geometric sequence is going to be of the form a times r to the n from let's say n equals 0 this time up to infinity, right? And it's a little different. We have n equals 0 as our base. And all that means is that the first term is always going to be a, and it's going to be a times r, and then ar squared, etc. Right? And so we want to see that uh, there will be three cases that we have to contend with. Right? And the first is r is greater than 1. Right? And so we want some a r to the n from n equals 0 to infinity. Right? Now the kth partial sum here is going to be, right? If we take a look at that, that's going to be, well, we start with s sub 0, and that'll be a. And then it'll be s sub 1 is a times 1 plus r. And s sub 2 is a times 1 plus r squared. Right? And s sub 3, yeah, we'll do one more. 1 plus r squared plus r cubed. And in general, right? In general, s sub n, our nth partial sum, is going to be a times 1 plus r squared all the way up to rn. Which we can rewrite this as a times the sum from n equals 0 to infinity of r to the n. Sorry, this is going to be let's make this k, right? I'm using too many n's. So s sub k, right? Alter this here quick. S sub k is equal to a. In fact, I'll just rewrite it. It's a times 1 plus r squared all the way up to r to the k, which really is going to be a times the sum from n equals 0 to k, right, of r to the n. Now, right, now we have to remember that in this case, r is greater than 1. So since r is greater than 1, the limit of this partial sum, right? Let's let k go to infinity of r to the n. Well, that's going to be 1 plus 1 infinite times, or something greater than 1, plus something even greater than 1, plus something even more greater than 1. right? And eventually it's going to blow up. And so whenever you have a geometric series where the where the ratio is greater than 1, that series is going to diverge. And to give you an example, just to kind of get a flavor for what this might look like, right? We can give ourselves a nice example. And it's going to be, let's say, 2 times 5/3 to the n, where n equals 0 to infinity. Right? And now we can move the 2 out, right? And that'll give us really 2 times the sum from n equals 0 to infinity of 5/3 to the n. And of course, looking at 5/3, right? So this is going to be 2 times 1, right? If n equals 0, plus 5/3 plus 25/9, right? Plus 125/27, and so on, right? And you can see that each one of these is larger than the last one, right? And that's because the ratio is greater than 1. And in general, the geometric series, like I said, diverges if r is greater than 1. Now, the next case is really the same case, right? So case 2 is if r equals 1, right? And this will also diverge for pretty much the same reason, right? So then if we have our series, there's going to be some a times 1 to the n. This is just going to equal the sum from 0 to infinity of a. So unless a is 0, it's going to just blow up, right? And so 2 out of the 3 examples diverge. But somewhat interestingly, if our ratio is less than 1, right, then we wind up with some fascinating behavior. Because if our ratio is less than 1, right, you notice, recall up here, right, as we take higher and higher powers of our ratio, it grows out of bounds. But if the absolute value of r is less than 1, then it's going to wind up shrinking as we get to as n grows, right? And so I'll give you a quick example of that. Let's say 10 times 1/2 to the n, right? Or not, yeah, let's even skip the 10. Let's just make it 1/2 to the n. Right. Well, we know that's going to be 1 plus 1/2 plus 1/4 plus 1/8, and so on. Well, that's going to very quickly approach. We can see that those terms are dropping off, right? At a rate much faster than something like the harmonic series. And in fact, the geometric series is whenever r is less than 1, will always converge, right? So this will always converge when r is less than 1. Right. Obviously, if r is like -3 or whatever, it will continue to just blow up. It'll just be wild. Right. Uh, and conveniently, this has a formula, right? So this convergence here has a nice formula. Right. Now, so let's uh, say we have this geometric series, a times r to the n. This will, so indicate r is less than 1. This is always going to be equal to a over 1 minus r. Right? And if you take nothing else from this lecture, which you should, but this formula is pretty cool. Right? And so let's give you a quick example of it, right? So let's see what 1/2 to the n looks like. Right? We want to add up every power of 2, every negative power of 2. Right? That's 1 plus a half plus a quarter, la di da di da. Right? Or we can use this formula that we've created and see that it's equal to 1 over 1 minus a half, which is really equal to 1 over 1/2, which is 2. Right? Or we can do something maybe a little more complicated. Let's do, let's say we want to get something that's pretty close to 1, right? Let's do 5/6 to the n. Right? Well, our formula gives us that this is 1 over 1 minus 5/6. We can do that because 5/6 is less than 1. Right? But that's equal to 1 over 1/6 is equal to 6. Right? And so in general, right, we can pretty much concoct any number we want out of a geometric series. Right? These things can get arbitrarily large according to what we want it to be. Right? If I wanted, right, let's say we wanted to find the geometric series of what's 9,998 over 10,000 to the n. Right? Well, that's going to be 1. Oh, this thing is, right? This is less than 1, barely. So this thing is going to be equal to 1 over 1 minus 9,998 over 10,000, which is really equal to 1 over 2 over 10,000, which is 10,000 over 2, which is equal to 5,000. Now, the upshot of this is that it turns out that infinite series are, we've seen so many examples where it's always 0 or infinity, right? Very rarely are you given examples where it's clear that a series or really anything can approach an arbitrary value and still be interesting. But it turns out that geometric series are this whole class of objects that can like a whole class of infinite series that can give you any uh, finite value from an infinite sum. And so they're pretty neat. Now, I want to finish the lecture just by talking about something that's pretty cool, right? I think these things are it's always a little bit of a delight seeing how something that looks difficult can wind up actually being quite simple, right? And so let's take a look at an example of what's called a telescoping series, which is a series whose terms cancel each other out. Right? And this is just a fun little example, right? So let's do the sum from n equals 1 to infinity. We want each term to be of the shape 1 over n over 1 over n, or 1 over n minus 1 over n minus 1. Right? As we kind of write out these terms, right? We see that the first term is going to be 1 minus a half. Our second term is going to be 1 over 2 minus a third. Right? Our next term is going to be 1/3 minus a quarter. Well, we'll draw one more term out just to make sure that everything's good. Right? So our next term is 1/4 minus a fifth, and so on. But now that this looks gnarly, right? There's a lot of fractions happening here. But we can see that this whole thing has a bunch of terms that will cancel out, right? So this half here cancels with this half here, right? Minus a half plus a half. And then we have minus a third plus a third. And then minus a quarter plus a quarter. And so the whole thing winds up canceling except the one. Right? So this whole thing is just equal to 1. And it, despite having this terrible looking presentation. And so when you're going through and experimenting with these things, uh, take the time to see, you got to determine what type of series we're looking at. And then from there, you can either use an argument using kth partial sums, or you can use the fact that it's a telescoping series or that it's a geometric series. Um, and yeah, and we'll go further into more techniques for analyzing infinite series in the next class. But until then, I think that's plenty for today. So thank you for tuning in, and I'll see you tomorrow.